Cookie break is at 3, not 3:30. If you come at 3:30, you'll all be gone. The reason is Julia needs to leave early to go to the parents' room. Which is why she went to be out of here by 4. It started to be really I'm free. Yes.
Just a question from partner. So 4th of July, does it mean that the groceries are closed?
No. It's like they may close a little early. Some shops they close. Okay. But by and large, most places are open. Right. Expect things to close early and most places are closed. So don't count with the buy and the US. Other than that. I'll do the sign and give the floor to John.
Okay, great. Well, thank you all for being here. It is my pleasure to introduce Dr. Megan Ansdell. So Megan is a program officer at NASA headquarters down in Washington, D.C., and we're so thankful that she could make the trip up for the day. So she is the AI and ML lead for planetary science and also a program scientist for the upcoming Habitable Worlds Observatory, as well as the planetary protection lead for the Mars Sample Return Campaign. So I expect we're going to hear about some of all that. Just a bit of her background. So she has a bachelor's in astrophysics from University of St. Andrews in Scotland, as well as a master's in space studies from the International Space University in France, as well as a master's in international science and technology policy. So great breadth. And that's from George Washington University down in DC. She then got her PhD in astrophysics at University of Hawaii, and then was a postdoctoral fellow at UC Berkeley in the Center for Integrative Planetary Sciences, and then a coveted ML research fellowship at the Flatiron Institute in New York City. So that was joint between the Center for Computational Astrophysics and Center for Computational Mathematics. So Dr. Ansdell is an expert in protoplanetary disks, as well as AI and machine learning at NASA, and also in science policy. She's won a number of awards, including the 2011 Sakharov Prize for Space History, her master's thesis in language protocols for international human spaceflight, won that award. She also received the Doctoral Student Excellence for Research Award from University of Hawaii, and also the PhD Prize for Planetary Systems in Bioastronomy from the International Astronomy Union. And then in 2023, Megan was awarded the NASA Early Career Achievement Medal. So has a very, storied set of accomplishments, and we're super excited to have her here with us to talk about enabling space science with large language models. So Megan, please take it away. And I think
All right. Can you all hear me? Okay. All right. Okay, yeah, so I'm Megan, and I'll be talking about enabling space science with large language models. And I'll start with some context to set things up, and a little about me. So John just went over a lot of this, but you'll get to hear it again. So I was actually born and raised in Hawaii, and I went to... Okay. And then I went to the University of St. Andrews in Scotland to get a bachelor's in astrophysics. After that, didn't really know what I wanted to do, but I know that I liked space. So I found this place called the International Space University. It's in France, and I did a master's degree in space studies. And if that sounds broad, it's because it is. So lectures on lunar geology, how to get insurance for your space launch vehicle, how to build a satellite. It was everything. And there I got interested in space policy and space law. So I went to GW and got a master's in international science and technology policy. And so my thesis there was on international spaceflight language protocols. So how do astronauts that often speak different languages interact while they're doing something incredibly difficult like space travel. At that point, I was told if I want to do science policy, I should probably do more science. So I went back and got my PhD in astrophysics back home at the Institute for Astronomy. And I studied protoplanetary disks and exoplanets. Then went to UC Berkeley for another sort of astroplanetary postdoc. And being in the Bay Area, obviously got involved with machine learning. And so that's how I ended up at the Flatiron Institute. I was only there for a short while, though, because I got offered the job I currently have now, which is a program officer, program scientist at NASA headquarters. And I'll talk a little bit more about what that role means in a little bit. But I did want to say a little bit about NASA Science first. So this is the science mission fleet chart that we have. So these are all the current and future planned missions, both to around our Earth, to the sun, throughout the solar system, and then, within the solar system, but looking out into the universe. So there's a lot of data that comes down from these missions. That data is very diverse in format, in scale, things like that. So, everything from rovers on Mars to things looking out, into the distant universe. I'm from the government, so I have to show an org chart if it's required. So this is NASA, and the Science Mission Directorate is often referred to as SMD. Get used to this acronym because I'm going to use it throughout this presentation. But basically, if you see SMD, just think all of NASA science. So the Science Mission Directorate is down here. There's 5 science divisions in there. So it's kind of probably hard for you to see, but Earth science, heliophysics, planetary science, astrophysics. And then just in the last couple of years, we got biological and physical sciences as well. So there's been a big push over the last few years to focus on, or to identify things that could be cross-divisional, so across all the science divisions. And so what are things that all the science divisions have to deal with? One of those is data. So just a few years ago, there was a new cross-divisional office called the Science Data Office, basically. It was established a few years ago, and they have sort of 3 components right now: core data and computing services. So, what do we need to actually house this data, cloud platforms, that kind of thing. Data science and innovation and machine learning is within that group. And then open science implementation. So they're very focused upon, training the community for the open science practices, being an advocate for that. Okay, so I said that I was a program scientist. What does that mean? It's a pretty vague term because it's a pretty broad role. So first and foremost, we are scientists, or at least were. We typically have a background in the assigned mission or program that we're working on. Program scientists come in several flavors. So one are for missions, so the things that go into space. And the role of the program scientist in a mission depends heavily on what phase the mission is in, right? Is it just starting out and you're doing concept development? Is it operating? Or is it, in its sort of post-mission phase? But basically, you're ultimately responsible for making sure that, the science that NASA paid for is what we're getting, and kind of overall responsible for the scientific success of the mission. There's also program scientists that manage RNA research and analysis programs. So this is everything from developing the solicitation to running the review panels. You recommend selections, and then you monitor the awards. And then there's cross-divisional efforts, and this is when you're sort of representing your science division at these cross-divisional initiatives. And program scientists can wear many, many hats. So usually you're assigned to several missions, you're helping out with several RNA programs, maybe you're involved in a cross-divisional effort, but it's usually a smattering, and that often changes with time. So these are some of the roles that I'm currently in black, and then the grayer text is ones that I've had in the past. But the one most relevant to this group is, as John mentioned, I'm the lead for AI and ML for the Planetary Science Division. I've also been involved in the past with the open source science group and managed the high-end computing resources for Planetary. As for missions, so I'm the program scientist for the Habitable Worlds Observatory. This is one of the upcoming flagship missions, so on the same scale as sort of Hubble and JWST. It's designed specifically to be able to detect life on another planet for the first time. And this is a early phase mission in the concept stage. I'm also the planetary protection lead for the Mars sample return mission. So this is leveraging more of my policy background. We're bringing samples back from Mars, and there's a whole bunch of things that need to happen to make sure that they're brought back safely and contained. And then in terms of RNA, I'm not managing any RNA programs right now. That's a little bit unusual, but it's because most of my focus is on those 2 missions right now. They're both flagship level missions. But I used to run the exoplanet research program for about 3 years until this year. Okay, so with that little background on what I do, let's take a look at the landscape of AI and ML and NASA science. So again, this is the scientific fleet chart, and I really wanted to highlight, just the diversity of data that comes down from here. And also, we have these RNA programs at NASA for analyzing that data, but I think, NASA as an agency primarily exists to send these things up into space. And so it's not just AI and ML being applied to the data that comes down from them, even though I think that's most commonly when it's been used. There's a whole, life cycle of mission development that I think machine learning can be applied to that's really exciting. So if you think about AI and ML at every step of the mission life cycle, when you're looking at mission development, you can use it for architecture trades, digital twins, getting ideas for hardware or technology development, exploring mission concepts. These things are very complicated and very interrelated with the science and the technology and the whole architecture of the spacecraft. And it's very hard to co-develop these things and update the entire, plan when something changes, right? So if you can get help with that, that would be great. For mission operations, there are things that you can do on board the spacecraft. For example, you can do autonomous targeting. You could do prioritization of observation. So the data downlink between a spacecraft and Earth is very, very small. So if you can start doing some of these things on the spacecraft, it can speed things up and make things more efficient. So you can get more science done with that mission while it's still operating. And then, of course, the science analysis part, this is where most of machine learning is applied to right now. The data comes down from the spacecraft, and these scientists are analyzing that data. And then there could be interesting things with post-mission opportunities. So, when these missions go on, especially if you think about like rovers on Mars, there are, probably millions of pages of operations logs from all the rovers that we've sent there. And, those contain things like, hey, we ran into this problem. We don't know what to tell the rover to do this or do this. They troubleshooted, they figured it out, it's there. And all of this stuff is recorded in these mission logs. So can you extract lessons learned, for example? Or a mission finishes, you have all the data, you have some, all these papers come out. Can you summarize what the remaining gaps are in scientific knowledge that wasn't addressed? And you can help, that could be used for future planning for future missions. So those are just some ideas of where AI and ML can help out. So another way to think about this is by looking at these wheels. So this is one for scientific research. This is sort of, the path of scientific research that we all learn sort of in high school. And the Science Data Office that I mentioned earlier has put together this data management wheel, where they use that to sort of think about, at each step of the science life cycle, how can data science techniques be used to make science researchers' lives a bit easier. What tools can be developed and things like that. So that's something that they've been using to sort of do their own planning and strategizing. And then recently, the chief technologist of the Science Mission Directorate, Carolyn Mercer, put together a similar wheel for AI and machine learning for flight missions. So this is basically what I said on the previous slide. But you can start sort of, seeing how these things are connected and see how things can be beneficial to the science researchers. Okay, so how is AI and ML being used currently for NASA science? This is a plot put together by Abby Ansari, who's in the planetary science community. She put it together for a white paper for one of our decadal surveys. And she keeps updating it every year, but this is just showing the percent of the published literature that's AI and machine learning. Her GitHub is there. I think the code is available, and she updates it there if you're interested. But there's some interesting things in this plot. Earth science is leading the pack, which is probably not surprising given there are many missions, much more data because their spacecraft that are closer to Earth, and more downstream applications, right? So it kind of makes sense. Heliophysics is basically keeping track with Earth science, which is really interesting. Heliophysics is a smaller community, but at least what I've seen of them, they have a very large and very strong and well-organized group of machine learning folks that do, I think, biannual conferences. So they've really sort of like decided to organize that community, and it seems to be paying off. Astrophysics was keeping pace until a couple years ago, so a few years ago. So I don't know why that is, but it'd be interesting to figure that out. And then planetary science, we're always just like a little bit behind. And I think, that's related to, some of the just how the planetary science community, approaches coding and things like that. And also just things that kind of are associated with a science community where, each mission is sort of is specialized to do a specific thing, and the data can be like especially heterogeneous. So I think that's part of the reason. But there are some core people in the planetary science community who are huge advocates for AI and machine learning, that are also very well organized. This plot on the bottom is from a survey that I put out to the Habitable Worlds Observatory, the other mission that I work on. We have an AI ML working group, and I put this out to the 144 people who signed up for it and asked, where's your area of expertise? Is it data-driven analysis, or is it more mission design, technology development? So I expected the data analysis to actually be much higher. But I think what this is helping to show is that, there is a growing interest in using machine learning for the more mission development, mission operations side of things, which I think is really exciting and probably where machine learning can have the biggest impact. That's basically what I just said. Okay, so in terms of what kind of initiatives and strategy that we have going on for NASA Science, most of what's been done over the last few years is something under the SMD AI ML initiative, and the website link is there. This group has been together since I joined NASA in 2020, and we've been there's basically a representative from each of the NASA science divisions, so I represent planetary science. And so what's been done over the last few years is we conducted sort of a survey of the community in 2020 to get an understanding of their expertise, their needs, their viewpoints, and this was sent out to every scientist, basically like at every NASA center, and a few other lists as well. So that was just to get an idea of what we were dealing with, and there were kind of no surprises. People were skeptical of some aspects of machine learning. Some people really needed training, right? It was kind of nothing new, but it's good to get that confirmed. And then in the next year, in 2021, we funded some individual use case projects from each of the NASA Science Mission Directorate divisions. In 2022, we worked on putting together training, like benchmark training data sets for each of the divisions. And part of that was also just like kind of demonstrating to our community what a benchmark data set looks like in their science field. Because you can show them like a general machine learning one, but they really, showing them what it actually looks like in their science field, I think gives them an idea of like what the standard is when you're looking at benchmark data sets.
Are you going to show us what those benchmark data sets are?
No, but I can send you guys the link or the link for that. Yeah, I don't have the slide on it.
Various machine learning problems are that would make it a benchmark. If you have a moment to say.
Yeah.
Mind repeating that question?
Yeah. One of the examples of the benchmark training data sets, I can't remember what the other ones were for the other division. 2 years ago seems like a long time. For planetary, we were looking at Cassini data, I believe. It was a semi-supervised like a data set for Cassini, and it was supposed to be used for ingesting, I think, in one of our data archives to help with search. But I'm probably getting a lot of those details wrong. The other thing we do is put on yearly workshops that are focused on different things. The one that we had this year was in March, and it focused on foundation models. So large language models were a big part of that. What I'll present on in a bit is the SMD large language model that was first developed at the end of last year, and that's continuing on now, trying to figure out different downstream applications and demonstrate those. Yeah, and then for this year and most likely into next year and the year after that, we're trying to develop foundation models for each of the Science Mission Directorate divisions as well. in terms of like an overall agency strategy towards AI and machine learning, there's been a lot of movement recently, mostly because the president told us to. So there was an executive order that went out a couple of years ago, and it's like 100 pages of telling all the government agencies that they need to start taking AI seriously. They need to have a chief AI officer. They need to be showing plans for using it responsibly and things like that. So we just named our chief AI officer in May, and he's putting together an AI strategy board for the agency. They just launched this resource hub where people across the agency can host events and share projects and things like that. NASA is intentionally spread across the entire country so that we keep getting funding. And that was done, back in the 50s and 60s. But it means that, a lot of these centers are kind of stovepiped, and it's actually quite hard to know what's going on in other centers. So we'll see where that leads. But there's been a lot of movement sort of more recently to, get our act together as an agency. Okay, so now I'll go into the NASA SMD LLM and do some background on LLMs in the beginning. But first, I'll talk about some of the reasons why we're doing this. Okay, so why should we even build a NASA SMD LLM? One, domain-specific LLMs will provide more technical depth compared to general purpose models, right? You can better support the downstream applications. And while there are domain-specific LLMs like SciBERT and BioBERT, no model existed that covers the domains of the Science Mission Directorate, right? Which are quite diverse, Earth science, planetary, heliophysics, and the biological and physical sciences. For BPS, think like space station. They're dealing with that kind of stuff a lot. So large language models will enhance our data systems. So it'll improve, data visibility, data access, data usability. It'll facilitate new discovery pathways. So it, increases the awareness and availability and the use of the data. And we invest a lot on our data systems at NASA. So increasing that value is really important. And making the user experience also better is also really important. It'll also increase the research efficiency, so saving scientists a lot of time by streamlining their workflows. There's a paper that came out a few years ago showing that the data wrangling time compared to the actual science time on a given science project is about 80%. So we can get that down. We can, hopefully increase the pace of science being done, but also just make scientists' lives easier. So these are some of the reasons why we would want to develop something like this. The goals were to basically, enhance the Science Mission Directorate's capabilities while also, promoting AI and ML usage. So addressing some of the, some of the community aspects of it. So the idea was, instead of doing these sort of one-off AI machine learning projects funded through grants or something like that, if we could start offering more of an enterprise level adoption, the benefits will be more widespread, but also the buy-in, I think, will be more widespread. So you're trying to shift that mindset towards AI and machine learning in the science community. This can also help with ensuring that AI and ML is used responsibly for NASA science, and also just to increase interactions between and across NASA, the science divisions and the centers and everything like that. And also with the data repositories as well. So this video is just going through really quickly the GitHub account that some folks put together for training for LLMs. This was done at the workshop that I mentioned that was in March. So that's available on GitHub. But they dedicated 2 half days to basically taking everybody at that workshop through some tutorials on prompt engineering, RAG, teaching them about the different types of models. So this was a data science-y community, but not all of them, most of them were not familiar with large language models. And in terms of assumptions, when building this model, so, trying to recognize that LLMs are extremely fast-paced. Sometimes scientists complain about how the science that comes out these days is really fast-paced, but I think large language models completely dwarf that. So, build something that can take advantage of frequent releases of improved large language models and try and make things flexible. Also, there was a big focus on open science, so NASA's taking that very seriously. We have a lot of requirements around that as well, but also, you know, making sure that those are woven throughout whatever model is created, because that's really that's one of the big pushes coming out of NASA science right now. And then also, I think to recognize that, you know, LLMs, at least right now, are mostly expected to increase the efficiency of scientific discovery and the speed of it. So, you know, this is really sort of enabling scientists to do their job better and easier, rather than, you know, replacing them, for example. And also recognizing that the benefits are not just to the scientists, but also on the data provider side, you know, the folks that are repositories that are building the tools to make sure that everybody can openly access NASA data. And then these are just some, you know, examples, sort of like generic examples of downstream applications. So for the science research side, improve data search and discovery in our repositories, quickly relate your new discovery to the current state of knowledge. You can, you know, perhaps use a chatbot to brainstorm hypotheses generation or design of your experiment. Some folks are actually already doing that. You can also, you know, use it to perform basic analyses and visualization of your data. Some folks are also already doing that. Or, you know, summarize some of your data notes, generate an abstract, that kind of thing. For the mission and program management side, so more like the side of what I do, you know, for the people running our data archives, I talked about, you know, increasing data utilization and visibility. But also, you know, if we're writing a strategy for the future of exoplanets, we can use these things to summarize the current state of knowledge, identify knowledge gaps for future missions. This can be integrated, you know, into planning. I mentioned before about these logs from rover missions that are available when the mission is closed down. You know, could you use those for troubleshooting for the next mission, or, you know, bringing out lessons learned from that as well. And then another thing that program scientists do, spend a lot of time doing at NASA headquarters, is organizing review panels for proposals. And, you know, if we could have something that could help us with, you know, even organizing them into thematic panels, matching reviewers with, matching proposals with, you know, reviewer expertise, that would save a tremendous amount of time. Okay, so for the large language model, I'll just do a background. I'm not sure how much background you've all gotten. So if I'm saying things that are, you know, that you all know, just tell me to move on. But for large language models, so these are, the modern ones are based on transformer architectures. These excel at processing sequential data like text. And that's because they use these things called self-attention mechanisms that are really good at capturing the dependencies, relationships, and importance of the different parts of an input sequence, like words of a sentence. It also enables parallel processing of the input sequence. So unlike previous architectures, which did sequential processing, so this makes it more computationally fast and efficient for downstream tasks, especially ones involving large data sets. So I'll talk about encoder versus decoder models. So two different types of models that are suited for different flavors of tasks. Encoders are bidirectional transformers. So they benefit from the understanding the information ahead and sort of behind the given input. And it changes these inputs into things called embeddings, which are basically vectors. And they're really good at, you know, processing input that's language and capturing the semantic meaning and the context of that input. So they can sort of like read and understand, but they can't like write and speak. So that's what decoders do. They're unidirectional transformers, and they're specialized in generating outputs like answers to a question. And decoder-only models will use the input of a sequence directly. If a decoder can also accept the output embeddings from an encoder. And in that case, this is an encoder-decoder model. Those also specialize in generating outputs, and they're particularly good when the output heavily depends on the input. So like when you're translating between two languages, for example. So these are, because of, you know, all the things I just said, they're better suited to different types of tasks. So encoders are better for more specific, they can be trained to do specific, more discriminative tasks. And they're good for tasks that require a very good like contextual understanding. Decoders are better for text generation tasks. And they're more flexible and sort of like more creative, but you have less control over them. So that's why things like hallucination happens. But you know, both are great at what they do, but they for different reasons, right? Okay, so I'm showing this because it'll be relevant for the NASA LLM on the next slide. But for pre-training and fine-tuning these models, the first phase you can think of as self-supervised pre-training. So you don't need extensive labeled data sets for this. It can use mass language modeling. So it's predicting mass words based on only on the context. So you get a really rich understanding of the corpus without needing data labels. And then if you include scientific documents in that corpus, the model will learn to represent in a more suitable way for scientific tasks down the line. The next phase of this would be downstream task fine-tuning. So this takes your pre-trained model from phase 1 and it fine-tunes it to a more specific task, and it uses a small task-specific labeled data set to do that. And the way that works is you can take, it's called a task-specific head. You add it on top of your pre-trained model, so the layers, and then you fine-tune on that task-specific data set. And so what this allows is adopting, the broadly learned representations from the pre-trained model to the nuances of a specific task. So that's what we did for what they're calling the Indus encoder-based model suite. This is the NASA SMD LLM that I've been referencing. And so in the first phase, they built an encoder-only model for just natural language understanding tasks. And they used a extremely curated domain-specific corpora, and I'll talk about that in a little bit, to pre-train the model. So this was documents from across the NASA science divisions. The second phase was to fine-tune the pre-trained model into a sentence transformer. So they did this using sentence pair relevancy, and they also used a curated data set for that as well. So I'll show the results of these models, but that's a high-level view of the work that was done at the end of last year. And the sentence transformer is just one of the possible fine-tuned models to come out of that base model from phase 1. So they're currently working on developing more of those. So this is the base model, and it's on Hugging Face. I think, yeah, the link is on the bottom right if you want to take a look. But this was a domain-adapted encoder-only transformer model that's capable of supporting potentially many downstream science applications. So it performed better than general models, as well as more sort of like sciencey models as well. And there were 2 benchmark data sets that were developed that were new for this. There's one for named entity recognition that's focused on earth science, in particular climate change. And then there was an extractive question answer data set as well that was used for the benchmark. As I mentioned, so for that one, for the training, they developed this curated domain-specific corpora for the training. So this is just summarizing it. But it was a data set that spanned all of the 5 NASA science divisions. And the top one is a metadata repository for earth science. The next 2 are geophysical and meteorological journals. So these are full papers. Also the English Wikipedia, PubMed abstracts and papers. So this is more of the biomedical field. And then NASA SciEx, which used to be called, I think still is, I don't know if they've actually made the switch, but it used to be ADS. And if you're an astronomer in this room, you're probably very intimately familiar with that. They recently expanded the reason why they're called SciX now is because they expanded from astro to helio and planetary. So that was the biggest source of information. It has, you know, all the papers going back to as long as you can think of for that.
Quick question. It looks like, at least going from the bottom, the first 4 or 5 are all public data sets. Are the AGU AMS papers and the NASA CMR also public, or?
I'm pretty sure they're all public.
Okay, all
Yeah.
right, thanks. And was this size limited by available computing, or, I mean, is there more to be had, or is this pretty much all?
This was, I mean, it depends. So, you know, this was mostly focused on science papers.
Yep.
And this is pretty much it.
Okay.
But we didn't dive into like mission logs or,
Okay.
you know, other documentation, right?
Right.
Partly because it's not straightforward to know where to get those.
Right. Okay.
There's also like a NASA technical server that has a bunch of things as well, potentially. So there's more things that can be done that aren't necessarily like science research
Right.
papers, right?
Yeah.
But are more like mission related.
Okay. All right. Thanks.
And one of the, you know, part of the reason, like, for example, grabbing everything from ADS or SciX, we needed their help. We worked and I believe somebody from there is going to give one of the plenary
Roberto.
lectures in yeah. So I'm not going to talk about that because he'll cover it. Okay, so this is the sentence transformer that was fine-tuned from the base model. And it was for information retrieval. And it also, you know, did well compared to other models before it. And there was a new benchmark data set that was developed called NASA IR as well, and I'll show a little bit about that. So the way that this was done, they basically pulled, with help from SciX and ADS folks, they pulled paragraphs from papers in the scientific literature, and then they had subject matter experts provide 3 question and answer pairs per paragraph, and ended up with about 500 pairs in total. So about 400 were used to train, and then 100 were reserved for the validation. So I believe this data set is publicly available as well. Okay, so one of the things for downstream tasks for using these 2 models is through something called the Science Discovery Engine. So this is something fairly new that's been put out by the open source science group. It's very much a prototype, the design, the SDE in general, and then also this application. So SDE was envisioned a few years ago, or it started being developed, and it's basically trying to unify all the search across NASA documents, metadata, software and tools, so code. And so it's geared towards, you know, the scientists using it and also the data repositories that are feeding into it. But, you know, NASA Science data archives are very much like spread all over the place. And that's because, you know, the science divisions were historically pretty stovepiped. And also there's just, you know, science data is very technically complex and difficult, right? So you need to have data centers that are very specialized to certain types of data, and that can vary greatly even within a science mission directorate. So the data is often spread all over the place. And then that's not even thinking about like the software and the tools that are used to analyze that data. So this was trying to get everything sort of in one place, so you could search something and bring up, you know, everything we would need to know, rather than looking at individual archives and things like that. So this neural search prototype uses retrieval augmentation generation to pair the encoder with a decoder. And the idea is to, and it was paired with a decoder through Langflow. I think the video is on the next slide. Yeah. Oh no. All right, well, you're going to see the video. This video was about just going through the prototype for SDE. So, you know, as a user interface, type in the search, it would spit back out snippets of documents that, you know, think can answer your question. Highlights the area where, you know, where it's finding it in there. You can click on that document and actually like see the source document and bring it up right immediately. That happens, you know, basically instantly. So they just went through a few examples of that. So we had people starting to play around with this over the last few months. SDE is going over a big like re-architecture overhaul right now. And when it comes back out, this will be in it as well. Still prototype, but the public will be able to use it. Okay. So in terms of where we go from here, so we have, this base model, we have a sentence transformer, we have a prototype application. Everything's very new. This all happened in the last like few months. So we were able to release these initial versions. There was a really successful training session at the AI workshop we had in March. And now the focus is on developing these downstream applications. So that process has been going on. It's been, I think, to be honest, like a little slower than I think the developers of this model would have liked. Partly because, a lot of scientists don't know what is possible, and they don't necessarily understand like the technical difficulties, right? They can have these great ideas, but like actually implementing that is difficult. So part of that is more of like an education thing on the scientist side as well. And then also, trying to make this not just like one-off applications, but actually operationally deploy it, possibly in the science discovery engine, for example. Okay, so with that in mind, what are some, challenges and takeaways from this experience? I think for challenges, you can kind of think of it in three categories. So the data is one of them, the tools you're using and the workflows are another, and then people. So for data, trying to find appropriate curated data sets for training or validation has been really difficult and very time consuming. As I mentioned before, the data across the Science Mission Directorate is very heterogeneous, not just in terms of format, but also physical scale of what you're looking at, the wavelengths that you're looking at, the targets, all the metadata. That's incredibly extensive and very different for every data set almost. And then data access. So as a government agency, we're required to have open and equitable access to the data and compute resources and models. And that's very difficult to ensure when your target audience is everybody. And in terms of tools and workflow, I mentioned before, recognizing that LLMs are, developing so quickly, and government things go slower. So how do you reconcile that? How do you integrate this into existing workflows? So a lot of missions have already set up their workflows. A lot of data repositories have, very ingrained processes on how to do things. And how do you insert this rapidly developing tool into that? And also, space missions usually take at least 10 years to develop, right? So how do you plan that far ahead when something's changing so quickly? Let's see, another thing, so transitioning to deployment, I'll talk about that a little bit on the next slide too, but there's this analogy to the technology readiness level gap where you can go from this proof of concept and prototyping, and then there's like this chasm where a bunch of things die before you get to like production and mission deployment. And we're sort of hitting that right now. And if we don't move over it, that could be detrimental. And then in terms of people, education, training, retention, people have to learn new skills. They don't have a lot of time. They're tired. And also just, building trust with AI and ML. I'm sure you all know this. And then also, these types of projects require interdisciplinary teams with sustained support over many years. There's just not a lot of funding mechanisms out there to support that. So those are some of the key challenges. And I'm just highlighting something that came out of our second AI workshop back in 2023. We were trying to, discuss what to do about this, analogy to the TRL graveyard. And there was a bunch of discussion around using knowledge management-based approaches that combine basically the three challenge areas that I mentioned before. And that's like a feature of knowledge-based management. And don't ask me any more about that because I don't know anything about knowledge-based management. But it's an interesting idea that it was like these three categories kind of mapped, to the same ones as those challenge areas. Okay, in terms of the LLM, I think basically there's two main takeaways. So, a comprehensive model suite that includes both encoders and decoders is really essential for getting diverse enough downstream applications in science. especially when we're thinking across of the Science Mission Directorate. And also this approach that NASA SMD has sort of taken about developing these SMD specific encoders and then pairing them with existing generative models like RAG. It's cost efficient. It's sort of more like bang for your buck when we have limited funds and things like that. And it's a pretty low risk strategy. And it's been shown that it does, it does enhance content generation and information retrieval. So there's really no need for us to make sort of a bespoke SMD generative model in that case. So the focus now is to really look on using RAG to develop these downstream applications. How much time do I have?
Let's say another 8 minutes or so.
Perfect.
Well, I mean, you have 20.
Yeah,
total.
basically with Q&A, you have 20.
With Q&A.
Perfect. Perfect. I didn't go through this presentation before, so it's always nice when you nail the timing. Okay. So I'm going to end with talking about one of the other projects that I work on called the Habitable Worlds Observatory, and how machine learning and LLMs can be integrated in here. So just some background. So HWO is the next flagship mission that was recommended by this thing called the Decadal Survey, which comes out, surprise, surprise, every decade, that plans like for the next 10 years. So it was one of the top priorities coming out there. And you can think of it kind of like a super Hubble. So it's going to be like Hubble, but bigger. And so it's going to look in the IR, the optical, and the UV. And it's going to perform a wide variety of astrophysics. This is what flagship missions do. They are meant to be like what we call great observatories. But it's designed specifically to search for signs of life in Earth-like planets or on sun-like stars outside of our solar system. And this is just sort of saying a bit more about that. But the idea is that, if you're going to develop a telescope that's capable of detecting biosignatures in the atmospheres of Earth-like planets around sun-like stars, and like a significant number of them, the technological advancement that you need to get there is going to mean like huge breakthroughs across all of astrophysics. So this mission will be able to directly address 2/3 of the 24 key science questions in the Decadal Survey, and indirectly address pretty much all the other ones. So it's pretty exciting. Another feature of HWO that was also a recommendation that came out of the Decadal Survey is for early and integrated mission concept maturation. And what I mean by that is that even though this thing is not going to launch for the next 15, 20 years, start developing the technology and the science and the mission architecture all together in an integrated fashion. And it might be a surprise that that's not how things are typically done, but involving the scientists and getting them to work really closely with the engineers this early on is something that's really difficult and hasn't been done, but it's now recognized that like that really needs to be done. So that's what we're doing right now. And this is just one of the simulations of what HWO can see. So that's a sun-like planet that's being occulted by a coronagraph, and you're seeing the planets going around it and what could be detected. So it's really exciting. There's a lot of people that are involved right now, and I think the next slide is going to be on that. But yeah, this idea is to really like co-develop the science, the technology, and the architecture all together from very early on. Oops. There we go. Okay, so one of the ways that we're doing this is we set up a whole bunch of working groups that literally anybody can join. And this was the first time that this was sort of done, especially this early in the mission. So we rolled out these working groups at the beginning of this year. And you can see there's science working groups, there's technology working groups, there are joint working groups that span science and technology. And then there's more like non-technical but community-focused working groups. So yeah, we put this call out to see if people wanted to join, and we had no idea how many people would join, and 1,000 people joined. So that's been interesting. And they're all now sort of hitting the road running, getting their work done. And their work will continue over about the next year. So one of those working groups, I guess I can go back and see, one of the working groups, the joint working groups, sort of middle towards the bottom, is a AI machine learning working group. I'm co-chairing that with Bruce Dean, who's at Goddard Space Flight Center. So for this group, we're really, looking at a lot of what I've been talking about before, just seeing where machine learning can be applied at every stage of the mission lifecycle. And we have a great steering committee from people from a bunch of NASA centers, JPL, industry, and also academia, and ground-based telescopes as well. So it's a good group. And basically what we're doing over the next year or so is putting together a bunch of white papers to sort of, set the landscape of like what's going on, what's applicable, where can AI and machine learning help. They're interacting a lot with the other working groups to bring them in and get their thoughts on things. There'll also be an overall white paper with a sort of strategy on how to keep HWO like AI ready from now until it launches. And also some use case demonstrations as well. A lot of what's the products are limited by is one, time, they have now less than a year, and two, they're all volunteers. So that will change in the future, but for now, the community working groups are mostly volunteers. So that's an idea of what we're doing. And one of the things that we do not have on the steering committee and the larger working group is LLM experts, language model experts. So I think, I was really excited to come talk to your group and get people interested because I think there's a lot that can be done. And we just happen to not have the expertise on the working group right now. And one idea that I've been kicking around is to have something that can rapidly explore the HW science cases. So what I mean by that is all the science working groups are putting together these science case development documents. And this takes a science goal and a science objective, which is in the decadal survey. And then they are trying to figure out what physical parameter can address that science objective. So like the size of a galaxy, right? And then what observable needs to get that physical parameter. So like a magnitude, of the galaxy or something like that. Sounds easy or simple, I guess, but it's really complicated and it takes people a really long time, like, months just to get one of them done. And you can think of it also like a tree structure. So like one science goal could have several science objectives. Each science objective could be addressed by, several physical parameters. Each of those physical parameters could, be achieved by an observable. So you can see like a very quick tree structure that gets pretty big. And so I'm wondering if something like an LLM could be used to basically explore that tree structure. And even if it's not specific, certainly accurate, it could at least give us an idea of like, where are the bounds and like, how far can you go with this? And you can start seeing trends in like what observables are needed, right? Which ones come up a lot compared to others. So we'll have actual science case development documents that the working groups are producing right now on the order of like 50 to 100 probably. And then also this, science goal to observable is kind of the flow of a scientific paper as well. And I mentioned before, HW is going to be a lot like Hubble. So also wondering if the scientific literature out there that has 30 years of Hubble papers could also be used. And I think that is my last slide. So I'm happy to spend the rest of the time with discussion.
So much. So if you have a question, please raise your hand and I will deliver this microphone to you for the benefit of our online viewers.
Hi, Megan. Great talk. Thanks very much. I am curious if you can talk a little bit about how NASA is thinking about risk analysis with LLMs, especially as it pertains to operations, not necessarily sort of data analysis, but operations.
Like operations of a mission?
Sure.
Yeah. Sorry, it was security, was it?
Risk analysis.
Yeah. So, I mean, I think it would, I'm guessing it would follow the same processes as you would with any other like technology. So, there are like TRL levels that you have to go through, right? And reviews that have to be done, right? So I imagine, if something related to, LLMs or machine learning in general were actually put on a mission, there's extensive reviews throughout the life cycle that, that do have a risk analysis. And I think it would just fit in along with the, the usual technology development life cycle.
Can I ask a follow-up question? Okay, everything I know about TRLs, I learned from Grant Tremblay's tweet about imagine there was a unicorn. You know which one I'm talking about. So I'm not super fluent in it. But given the levels of vetting and analysis, could would a mission be using current LLM technology, or given the level of vetting that's required, would they be using old technology because it had been able to go through the whole technological assessment process?
I mean, so if it's something that's on a spacecraft, right? I mean, you can upload software, right? So the big difference is like making sure that the spacecraft can actually do that processing, right? So I was talking to some folks earlier, and you know, the current like chips that we have on spacecraft can't handle that. And there's new ones coming out that like hope, you know, coming out, I mean like 10, 20 years, you know, kind of thing, they might end up on a spacecraft. But that's generally like the limiting part of it. I think when you have a $10 billion mission up in space, you don't want to be uploading new software like frequently. So, you know, I think it'll never be in the, you know, I wouldn't say never. It won't be in the critical path the first time you fly something, right, with an LLM or any machine learning kind of thing on there. They'll probably be testing on, you know, CubeSats, for example, or like smaller satellites, right, before you put it on something like HWO.
Got it.
Yeah.
Thank you.
Oh, Sandeep.
Thank you. I don't know if the answer to this might require going back to your org chart, but I was thinking about, like, you know, a lot of the data that went into training Indus and the current LLMs were reports, papers, what I would call, like, you know, monologues. They were written by some person for an audience or something. I was interested in, like, you know, dialogue type data, like, you know, logs of either design processes where a bunch of engineers are sitting down and trying to figure something out, or even during flight operations, things that go on. There's a lot of expertise and experience that lives in that kind of documentation, which then can be used. So which part of NASA, if any, would want to work in that space? Because one of the things we do that's special over here is we look a lot at interactions using language.
Yeah.
So some thoughts on that. And then I had another follow-up about what you said something this morning about the Mir mission, which had to do with, maybe I'll ask them both at once. We also have a lot of expertise in multilingual systems. So I was thinking, is there any, how much interest is there in enabling multilingual conversations in the mission design phase, in the mission operations phase, or any other phase? Because that's another space where we do a lot of work. So two questions, yeah.
So for the first question, I'll just say I've never had a request to go back to an org chart. So. Sorry, the screen in here went blank, so this might take way too long. I don't want to give you guys a seizure.
No, org charts are interesting.
Yeah, they can say a lot.
Yeah.
Okay, we're nearly there. Let's see. So you'll see, let's see, where would it be? So here, the chief technologist.
Yeah.
And then in each division, there's also, so like there's a Earth Science Technology Office, the planetary one. Yeah, this is the Planetary Technology Office. Okay. So those are the ones that would focus more on like the mission development operations kind of side of things.
All right.
And, you know, I was really interested in getting the rover operations logs, and I did ask around, and I was surprised that people were like, I don't know. But I didn't do too much digging, but like those should be available somewhere. And it would be interesting because I think a lot of it would be like conversational, right?
Yep.
Rather than like someone's summarized thoughts, you know, after lots of thought and analysis. It would be very like it would be very much of like a conversational flow trying to figure something out.
Right.
So, you know, I think that kind of information, we can talk more about like where to get it. I think it would be with the individual like missions rather than like, or in one of the like technical servers probably.
Yeah, I would expect as much, yeah. In fact, the big initial effort might be to just put it in some digital form that's usable, go through the processes to make it accessible, yeah.
But those technology offices are the people who'd probably be the best to talk to about the context and the background and like what might be useful in the future.
Okay.
They think more strategically about that kind of stuff.
Okay.
Yeah.
And then thoughts on the multilingual aspects?
Yeah.
Is there a lot of international stuff that happens, or?
There is a lot of international stuff that happens. I will say, like in the sciences, like we're spoiled. People just speak English, you know? So, I mean, I think I think it'd be great for thinking more about like inclusion to have tools like that available. Like I could see our open science folks being really interested in something like that because, you know, you can say, well, everybody speaks English, but not everybody speaks English. And like being able to learn a second language is like a privilege, right? So it could open things up to people who normally wouldn't be able to participate in things, right? So I think the open science folks, I think, would be really interested in that.
I just want to get your thoughts actually. So, do you think that some of like the biggest, I guess, gains from AI in the mission development space is just through automating like the boring stuff, whether it's, you know, fixing data formatting or doing emulation of something that would otherwise be hard to do, or is it like some like big major impacts on the design of a mission, which is having like an LLM synthesize or generate novel ideas, that kind of stuff?
Yeah. So I think like the boring stuff would actually like have a huge impact on people's like just work balance, you know, like taking a bunch of work off of people's plates that can be automated. I think like we were talking earlier, but like I interact with loads of scientists through my job and people are just burnt out, you know, and like getting a little help would, I think, you know, it might be boring stuff, but I think it would have actually a huge impact on scientists' lives. And then, you know, for the most like exciting part, I think there's some people on the working group, the AIML working group for HWO that are working on generative designs. And so like, that's the kind of thing that I think is like the most interesting and could have the most impact. So trying to design these, you know, coronagraphs, for example, right? It's like incredibly complex and people do get kind of like stuck in like a certain way of thinking. And so these generative models can help with like, you know, popping out an idea of a different design. And maybe it doesn't actually technically work, but it can like trigger a different like thought path, right? So that's tough to me, especially, you know, for HWO where it is now in the concept development phase, is the most exciting for me and could have the biggest impact, right? Especially like very early on. Yeah.
Yeah. No, thanks for your thoughts. Any other? Oh, question back here.
Thanks. Thank you very much for your great presentation. I was just curious to know your opinion about, is the scaling a bottleneck for NASA? Like the fact that we are scaling large language model to more and more data, we need more and more compute resources. Do you think that, according to what you know about NASA, do you think that you are capable of creating your own large language model from scratch, or do you really need to fine-tune them to sort of find efficient method to do it?
Yeah, I think scaling is a big issue. So for the large language model that I presented, that was done in partnership with IBM Research, which I should have mentioned earlier. But we were using their compute, you know, we were using the expertise that they had, right? You know, we do have like supercomputing clusters at NASA. Not many of them have GPUs, you know? And so like, I think another aspect of it is, you know, we are required to make everything openly available and accessible as possible. So if you have a huge model that people can't, you know, people can't use, but it's also, you know, it's somehow being used for NASA science or something like that, you know, it kind of isn't consistent with our open science policies and practices. So that's another issue with the scalability as well. So.
Okay, thanks. Any other questions? And also mention just like the entirety of the astronomy literature is like 2 billion tokens. So from a data scaling up standpoint, I think we're not really able to train super large language models anyway because it's just very inefficient. Oh, Mark.
Actually, on this topic, I saw that you had the wiki data there with 5 billion tokens, and the astronomy data seems to be 6 times larger. So is there, because there is simply more text, or the data is encoded in some, let's say, more token demanding way?
I am not sure. Yeah, you're reaching the limits of my involvement in the project and my technical expertise
Okay.
on this
Thank you.
specifically. I can ask though. and get you an answer. for that.
Just a curiosity question, nothing like really important, but thank
Actually,
you.
John might know the answer based on his other work that he's done related to.
No, I don't think I know the answer to that specific question. Yeah. All right. I know we're coming up on lunchtime. So any last questions or forever hold your peace or ask Megan during lunch
Oh, ask me later. Yeah.
or keep conversing during lunch. Okay. Well, why don't we break for lunch? What do you think?
Yep.
Okay. Okay. Well, thank you again, Megan, for this wonderful talk.
And I don't know if lunch is here.